I welcome you all in the lecture of Dr. Rajendra C. Jadeja. Dr. Rajendra C. Jadeja is currently working as an Associate Professor of Inorganic Chemistry in the Faculty of Science, the Maharaja Sayajirao University of Baroda, Vadodara. He has a more than 17 years of research and teaching experience of UG and PG level. He has successfully guided 5 research scholars and currently 7 are working for their PhD degree in chemistry and in environmental science. He has published more than 70 research papers in the Journal of National and International Repute. He is also a author of several book chapters. Tuaska's Visiting Scholar, British Ecology Society Visiting Fellowship was awarded to him for doing advanced research. He is also active in administrative work and is Associate Director of Environmental Studies Department of same university and Dean of Students of the Faculty of Science. He has also experience in developing and executing MOOC courses of undergraduate students of chemistry on SWAYAM platform. His area of research interest includes coordination and bioinorganic chemistry, environmental chemistry, and marine pollution ecology. He is also associated with Indian Chemical Society ICS Kolkata and Indian Council of Chemists ICC Agra, and currently holding a position of Honorable Secretary of Vadodara chapter of the ICS and also council member of the ICS between 2020 to 2022. Thank you.
Hello friends, we will be talking today on the electronic spectra of transition metal complexes. This is my lecture plan. We will be talking about the color in the transition metal complexes, different types of spectra. We will be talking in particular about electronic transitions. We will also see some of the selection rules. We will also discuss about the coupling of orbital and spin angular momentum, and finally about term symbols and the various electronics transitions. Friends, as you know, the chemistry of transition elements is very colorful chemistry. You have come across the various metal salts which we use in our laboratory. This is some of the metal salts, of which some are very colorful and some are white in color. The colorfulness of these complexes is because of the electronic transitions taking place in this compound. Today I am going to introduce to you the colorful chemistry of transition metal complexes. Not only in the solid state but in solution state also, these complexes are giving a color of various intensities, and different colors are observed, in particular with the change in the oxidation state of the metal ion. All of you are well aware that when we do practicals, the manganese, because of the various different oxidation states, gives different colors. So today we are going to discover the science behind the various colors observed in these transition metal complexes. As such, you are aware about the science of the color. That is to say, when white sunlight will be falling upon any compound, then part of some of the light will be absorbed by the substance and the remaining light will be reflected back. So the color of the compound is because of the whatever light is not absorbed by the complex, but it is the complementary color of the light which has been reflected back. Say for example, if the red color is being absorbed by the particular compound, then as shown in this artist wheel, the complementary color to the red is green, and therefore the compound will be appearing green. There are various nomenclatures have been used in the various texts for the electronic spectra, namely electronic spectra, DD spectra, UV visible spectra, ligand field spectra. These various nomenclature, as all of you know, is because of in this electronic spectra, the transition of electron is taking place, and therefore the name electronic spectra. The word DD transition is also well aware to all of you. When electron is jumping, it is jumping from one d orbital to another d orbital, and therefore the name DD spectra. It is also called as UV visible spectra because when electron jumps from one d orbital to another d orbital, the resultant transition fall in the region of UV as well as visible in the electromagnetic spectrum. This particular spectra of transition metal ions are mainly affected by the ligand, various ligands which is attached with the metal ion, and therefore the term ligand field spectra, because the intensity as well as the position of the spectra changes with the change in the nature and number of the ligand present into the metal ion, and therefore the name ligand field spectra is also appropriate to this particular electronic spectroscopy. So therefore there are various names for electronic spectra is there in the literature. The technique as such is very simple. All of you know we require a UV visible spectrophotometer which is having a one light source. Sometimes it's a tungsten lamp which gives the energy corresponds to visible range. However, deuterium lamp gives the light corresponds to UV region. In present days, the xenon flash lamp has been replacing the tungsten lamp, and therefore only single lamp is giving the energy source for both UV as well as visible light. The substance or the compound for which we wish to determine the spectra needs to be placed in a cuvette in a solution state. However, we can also measure the spectra in the solid state also in form of reflectance spectra. As all of you know, when light falls onto any solution, then some of that will be absorbed and the remaining light will be reflected back. So here the absorbance is measured, and therefore the Lambert's-Beer's law is observed in this case. All of you are very aware about this law, that A is equal to epsilon into L into C, where epsilon is nothing but the molar absorptivity, or it is also known as molar extinction coefficient. A is the absorbance, L is the path length. Generally we choose a 1 centimeter cuvette, therefore the path length is 1, and C is the concentration of the solution for which the spectra has been measured. Generally, to get a better spectrum, we record the spectra with very concentrated solution. After seeing the terminology about the recording of the electronic spectrum, let us now show you some of the electronic spectra recorded for some of the metal complexes. When you look at this spectra, you will observe that it's a very complicated. In some of the complexes, we have only one band, but in some of the spectrum, more than one band is also present. Also, this intensity and the nature of the peak in each of the spectrum is highly different, and therefore we can say that the interpretation of the spectra of transition metal complexes is highly difficult and requires an expertise. Although the recording of the spectrum is very easy, the interpretation is always challenging when it comes to the research scholar. And therefore, the analysis of the spectra is quite complex. If you look to this spectra, then you will see that there are three main features of the spectra. How many number of peaks are there? That is, will number of this peak in the spectrum that depends upon the electronic configuration of the metal center. At where this peak is appearing, that is the position, which talks about the wavelength as well as the energy, that can be determined from the ligand field splitting parameter, that is d octahedral or d tetrahedral, and it also depends upon the degree of inter-electron repulsion. Finally, the third thing is about the intensity of the spectra, and that is depends upon the allowedness of the transition, which is described by two selections rule, which we are going to see in the later part of this lecture. So therefore, we need to understand the three things about the electronic spectrum, namely the number of peaks, position of the peak, and the intensity of the peak in the electronic spectra of the transition metal complexes. Let us understand this in the following slides. As you know, the electronic spectra arises from the electronic transition between the T2G and EG molecular orbitals and are used to determine the value of delta O or delta T for the complexes. Change in the electronic environment can therefore sometimes complicate the spectra. As you can see in the slide, we have a two type of a environment, namely the tetrahedral and octahedral environment around the metal ion, and therefore the intensity as well as the energy in both this case will be different, because in octahedral there will be 6 ligand, while in tetrahedral there will be only 4 ligand, and therefore naturally delta O and delta T will be always different, and therefore the spectra recorded for each of these type of complexes will be different. Since the promotion of an electron from the T2G set of an orbital to the EG set can involve differing change in the electronic environment, three peaks of the different intensity will be seen in the spectrum. As you can see in this example, we have an example of a amino complex of a chromium, in which there are three types of a band is observing, namely one is spin forbidden transition, the other one is a spin allowed transition, and the last one is a charge transfer spectrum. If you see in the spectrum closely, then the first band which is observing in the UV region is nothing but a charge transfer transition, while the middle two are the spin allowed transition, and the last one is the spin forbidden transition. Let us talk about the charge transfer transitions in the electronic spectra. As all of you know, there are many complexes in which there is no d electron present. Say for example, TiF4 ion, in this particular TiF4 salt of titanium, there is no d electron present. Similarly, the other halo compounds of titanium, namely titanium chloride, titanium bromide, and titanium iodide, in all these compounds there is no d electron. As there is no d electron, therefore there will be no transition of an electron is possible, and therefore ideally if there is no dd transition, then this compound should have been colorless, isn't it? Similarly, in the case of zinc ion, in +2 oxidation state in particular, it is having a d10 electronic configuration, wherein each of the d orbital is occupied with an electrons, and therefore there is no chance of dd transition, because all the d orbitals is fully filled with an electron. Therefore, in this case also, we should not observe any dd transition, and because of that, the zinc metal ion also should have been colorless. The other examples which are described are about the permanganate ion and dichromate ion. In this both the case also, manganese is in the +7 oxidation state having D0 configuration. Similarly, the chromium ion in D6 chromium ion in +6 oxidation state having the D0 electronic configurations also should have the no DD transition, and ideally therefore they all should be white or colorless. But surprisingly, if you see some of the salts like bromo salts of the titanium or iodo salts of a titanium, they are orange and dark brown in color, while that of permanganate ion is extremely purple and dichromate ion is extremely bright orange in the color. As there is a color observed in this compound, therefore there must be, other than DD transition, must be responsible for the color in these compounds. As we have understood, it is because of the charge transfer spectrum. What is charge transfer transition? Since all of these metal ion is either having no electron or it is having its d orbital is fully filled with an electron, therefore there is no DD transition is possible, but they are attached with the anion or the ligand or the counter ion which are negatively charged, and they can transfer the electron to the metal ion, and once the electron which is charged species is getting transferred from ligand to metal, we can say it is ligand to metal charge transfer spectra. In fact, there are two types of a charge transfer spectra, namely ligand to metal charge transfer, as well as it can be metal to ligand charge transfer spectra. The intensity of these bands are generally very high in the electronic spectra, and they are observed mostly in the UV region. After talking about the charge transfer spectra, let us talk about the selection rules for electronic transition in the d metal complexes. As you know, the transition of an electron is mainly governed by the two selection rules, namely Laporte selection rule and spin selection rule. Let us discuss this one by one. The first one is the Laporte selection rule. This states that the transition where there is no change in parity or dipole moment are not allowed or it is forbidden. That is to say, G to G as well as U to U transition is forbidden, while G to U or U to G transitions are allowed. That is to say, Gerard to Gerard or Ungerard to Ungerard is not allowed or it is forbidden, while Gerard to Ungerard to Gerard is allowed transition. Now, when we see in the transition metal complexes, mainly the ground state is also Gerard, while the excited state is also Gerard. That is to say, whatever the states are arising in the transition metal complexes are Gerard to Gerard, and therefore all the transition in the metal complexes is in general Laporte forbidden because they are G to G, and therefore the intensity of the DD transition of these particular metal complexes should not have been very intense. However, if you compare the intensity of this transition with the charge transfer transition, you will see that the charge transfer transition, as I just now told before, are very intense. They are having very high intensity. This is because it is either P to D or D to P transition. That is to say, all the charge transfer transitions are Laporte allowed transition, and therefore they are highly intense, while the DD transition are Laporte forbidden because they are mainly G to G transition, and therefore they are having very weak intensity. The second selection rule is spin selection rule. If you see the transition in the electronic spectra of the transition metal ion, then most of the transitions are from or between the states having same spin multiplicity. That is to say, they are from either triplet to triplet or singlet to singlet, and therefore there is a no change in the spin quantum number, or the delta S is equal to 0. Such transitions are said to be spin allowed transition. However, if there is a change in the spin, or if there is a change in the spin of any of the states, say for example, if the ground state is triplet state and the upper excited state is singlet, so therefore here the spin changes while electronic transition is happening, and therefore delta S is not equal to 0, and such transition are said to be spin forbidden transition. Therefore, the two type of selection rules are putting the restrictions on the electronic spectra of transition metal complexes. If both of these particular selection rules is making the transition allowed, then in that case the spectra which is observed should be having very high intensity. But unfortunately, in the case of transition metal complexes, either of the selection rules is not allowing the transition to take place, and therefore the spectra which is observed is of very low intensity. As for instance, you can see in this slide, in this particular example of an aqua complex of nickel, you can see there is a charge transfer band or charge transfer transition which is having very high intensity, and therefore it is not recorded in this particular example, while you can see there is a DD transitions of having moderate intensity, because they are, although the spin allowed transition, but Laporte forbidden transition, and therefore having very weak intensity. Sometimes shoulders are also, very weak shoulders are also seen in the spectrum. It may be sometimes due to the violation in both the selection rule, namely they are spin as well as Laporte forbidden transition. After understood about the allowedness in the transition, we can conclude that mainly there are three types of bands present into the electronic spectra of transition metal complexes. That is Laporte allowed plus spin allowed charge transfer transitions, which are having very high intensity. There are transitions which is Laporte forbidden but spin allowed, that is D to D transition. As I told you in the beginning, they are between the states of same spin multiplicity and therefore spin allowed, but since they are G to G transition, they are Laporte forbidden, and therefore their intensity is moderate. And the third category of transition, which are Laporte as well as spin forbidden, because they are from between the states of different spin multiplicity, and they are also G to G transition, and therefore they are doubly forbidden, and because of that they are having very low intensity. My teacher used to say that if you wish to find this type of a spectra, then probably you need to use the magnifying glass, because they are hardly seen in the spectra because of very low intensity. So after understanding the selection rule of the electronic spectra, let us now understand about the energy level between which the electron is jumping from one energy level to another, which is responsible of giving the band in the electronic spectra. So the transition of electron from lower energy level to the higher energy level is due to absorption of energy or light in the either UV or in the visible region, and therefore in this case the electron is jumping by absorbing certain amount of energy. Moreover, there is not a single electron sometimes in the many of the metal complexes, because many of the metal complexes are having more than one electron present, and because of that an inter-electronic repulsion or electron-electron interactions is also responsible for complicating the spectra of the transition metal ion. Particularly, if you see in the periodic table, we have a three transition series, namely first, second and third transition series, and therefore we have a 3D, 4D and 5D series complexes. The electronic spectra of all these three series is highly different. In the 3D metal complexes or in the 4D and 5D metal complexes also, we have an electron present not only into the d orbital of the metal, but also the inner s orbitals is also full of an electron, and therefore the interelectronic repulsion must be considered in these cases. The electrons are not independent of each other, and the orbital angular momentum of an electron and the spin angular momentum of an electron also will interact with each other to give a resultant angular momentum, which is, we call it a J, and therefore J is nothing but it is a sum total of ml and ms. So therefore in the 3D series, the orbital momentum, that is ml value, and the spin angular momentum, that is ms value, interaction is very weak, and therefore this interaction is called Rosell-Zonder or LS or spin orbit coupling. While in 4D and 5D series, the orbital angular momentum ml and the spin angular momentum ms value interactions is very strong, and therefore in case of a 4D and 5D series metal ion, you can say that JJ coupling is operative, and therefore in case of the first row transition metal ion, the Rosell-Zonder or LS coupling scheme is operative, while in the later series, that is 4D and 5D series, it is the JJ coupling which is operative. After understood about the ml as well as ms and the role of spin momentum as well as the angular momentum in case of a electronic spectra, let us now try to understand the resultant states which have been formed, which we called it a microstate. As I just now described, the angular momentum of a various electron, when we make a sum total, then it will give you the resultant angular momentum capital L. Similarly, the spin momentum of an individual electron, when add up, will give the total spin angular momentum capital S, and therefore the states, which we call it a microstates, between which the actual electronic transition takes place, is designated by the value of L and S. Remember, the capital L and capital S is different than the small l and small s which we use for the single electron. Here the capital L and capital S are nothing but the sum total of angular momentum as well as spin momentum of all the electrons. And therefore, when we write this microstate, then we need to consider the value of L and S into consideration. Moreover, the J can be obtained by sum total of L plus S, that is to say, L and S coupled to give resultant quantum number J, where L plus S equal to J, called Rosell-Zonder or LS or spin orbit coupling. Individual L and S coupled to give individual resultant quantum number J, that is to say, L1 plus S1 will give J1, L2 plus S2 will give J2, and so on. That is called JJ coupling. So the JJ coupling will be operative in the 4D and 5D metal complexes, while the LS or spin orbit coupling will be operative in case of a first row transition metal complexes. After understood the difference between the LS as well as JJ coupling, let us now try to prepare the microstate chart for the electronic spectra of one of the metal ion. A microstate state table that contains all possible combination of ml as well as ms is constructed. Each microstate represents a possible electronic configuration. It It includes both ground and excited state and must obey the Pauli's exclusive principle. You are already aware about this term symbol, which is having a syntax 2s plus 1 Lj, where this 2s plus 1 is nothing but a total spin multiplicity. The capital L represents the total angular quantum number, and this J is the total resultant angular quantum number. So from the value of this term symbol, one can label particular state. As I told you, the electronic spectra are nothing but a spectra between the state of two different spin multiplicity, and the designation of this each state can be determined by determining the term symbol for the each states. Let us clear here that the different value of L, namely 0, 1, 2, 3, 4, etc., is designated by different symbols. For 0, it is S state, for 1, it is P state, for 2, it is D state, and so on. And therefore, the term symbol for the particular metal ion can be determined by determining the value of L, S as well as J. After understood the syntax for the term symbol, let us try to determine the possible value of ml and ms, as well as let us follow the Pauli's exclusive principle to set up the chart for the microstate of particular configuration. Say for example, in this case we are taking an example of a carbon which is having a P2 state or P2 system. As all of you know, the electronic configuration of a carbon is 1s2, 2s2 to P2. Therefore, since there is a 2p electrons is present into the carbon, when we construct a microstate table of this particular metal ion, then we will try to only look up to this P2 electronic configuration only, while the inner electron is not taken into account. So the microstate corresponds to the various possible combination of an electrons within the px, py and pz orbitals will be now the discussion in the further slides. As I told you, for this 2p2 configuration, the value of n is equal to 2, while that of L is equal to 1, while ml can have all values from plus L to minus L, that is minus 1, 0, plus 1. So there are total 3 possible values for ml in this case, while ms can have always either value plus half or minus half. So depending upon the different value of ml and ms, we can have a various types of different states of different energy. It is something like we have a 3p orbital in which we want to put the 2 electrons. In how many ways we can put this 2 electron into the 3 different p orbitals, isn't it? So here, this is the first way in which both the electron with the upward spin have been shown in this particular 3 orbitals. However, one can always choose the 2 different orbitals and again putting the electron in the same upward spin only. While the third way of writing is, I am putting one electron with upward spin and getting it paired with the another electron with the downward spin in the same orbital. Of course, these are the 3 different arrangement of putting this particular 2 electron into the 3p orbital. But let me tell you friends, these are the not only ways of putting 2 electron in this 3p orbital. We can write other possibilities also, which will give the complete microstate of the P2 configuration. So this configuration, as I told you, are called microstate, and they have different energies because of the inter-electronic repulsions. When we write the electrons in this particular fashion, or in this particular fashion, or in this particular fashion, then in all these cases, the inter-electronic repulsion will be different, and therefore we can have the different microstates of different energy will be observed. Say for example, now it is before you, we have this two electrons are having the different ml values and the different ms values. So these are the example of the sum of the ground state microstate. The other would have the electron arrows pointing down. So all these three are the example in which the energy will be minimum, and therefore we can say this is the ground state microstate. While this is the another way of writing the electron, wherein we are getting the electron pair into one particular box. Similarly, electron can be paired in the other box as well as in this box. So this is an example of some of the excited states of the microstate. So now let us see the complete table of microstate for P2 configuration. So for the electron in the same ml value and having different ms value can be written as 1 plus 1 minus. While when we are pairing the electron in the same, we can write minus 1 plus 1 minus. So here we can have a different possibilities of writing two electrons into the 3p orbital will results into such ml-ms chart, which we also can call it a microstate table. So this is a microstate table for the P2 configuration. Once the microstate table is complete, all the microstate associated with an energy state with specific value of L and S are grouped. It doesn't matter which specific microstates are placed in the group, microstates are grouped and eliminated until all microstates are associated with a specific energy state or the term. Say for example, in this particular table of microstate, let us eliminate the microstate with ml is equal to plus 2 and minus 2 with resultant ms is equal to 0. So those microstate are shown in the red in this table. So here in this table you can see that this microstate is having ml is equal to plus 2 to minus 2 and ms is equal to 0, and therefore all these 1, 2, 3, 4, 5 microstates can be eliminated. Now again let us see these 5 microstate, they are associated with the term 1d, because when the ms is equal to plus 1 and minus 1, that is equal to 0, the spin multiplicity, that is 2s plus 1, will be nothing but a 2 into 0 plus 1, that is 1, that is singlet state, while the ml will be having value 1 plus 1, 2, and therefore L value is 2, and therefore if you see in our table 0, 1, 2 like that, then for 2 the symbol D is to be used, and therefore all these 5 microstate is corresponds to singlet D. That is to say, singlet D is the for this particular 5 microstates, that can be eliminated from the table. Now let us see the one which is written in a green. So in this case, those which are written in a green, they are total 9 microstates. For these microstates, if you see, the resultant spin momentum will be, it is a triplet state, and therefore both the electron is having a plus half, or it is minus half, and that's why the total spin momentum will be equal to 1, and therefore 2s plus 1 will be equal to 3, and therefore all these states is nothing but a triplet state. And for all these electrons, if you see, the ml value, capital ML value is 1 plus 0, that is 1, and for 1 it is the symbol P is to be used, and therefore these all 9 microstates corresponds to symbol triplet P. Now when we eliminate those, then we have left with only one microstate, and that is only one microstate is remains in the table, which is associated with singlet S, because for this particular microstate, both the electron is having spin moment, both the electron is having ml value is equal to 0, and therefore when it is 0, it is correspond capital L will be also 0, and therefore corresponds to S state, and both the electron is also having, the one electron is having a plus, another is having a minus, that is to say the ms value is equal to 0 and therefore corresponds to singlet state. And therefore in case of a P2 configuration, we are left with three types of a microstate, namely singlet S, triplet P and singlet D. So now the next task to us to arrange these three states in a different energy, that is to say which one among these will be the ground term and which one will be the excited term. So to do that, we have a Hund's rule of spin. Hund's rule of we have to apply the Hund's rule. According to the Hund's rule, the first Hund's rule says that the states of highest spin multiplicity will always lies lowest. So among these three, only P is having a 3 spin multiplicity, that is triplet P, and therefore triplet P will be the ground term. Now out of the singlet D and singlet S, there are two such states, and among these two, the one which is having a highest value of L will be lying lowest. So out of the D and S, the highest value of L will be in D, and therefore D will be having lower energy, and the highest energy microstate will be 1s, and therefore one can arrange these three microstate of P2 electronic configuration in the order triplet P having a lowest energy, singlet D having an intermediate energy, and the singlet S will be the having a highest energy, or it will be the highest excited state. So this is how, by following the Hund's rule, one can arrange the different microstates into different energy. Also, if we apply the same way the calculation to the D2 electronic configuration, then for D2 electronic configuration we can get the 45 different microstate, because for D2 electronic configuration we can have ml value 4 to minus 4, and ms can again have value 1, 0 and minus 1, and therefore if we can construct the microstate table for D2 electronic configuration, then we can results into these 5 different microstate, namely singlet S, singlet D, singlet G, triplet P and triplet F. Now if you use a common sense, then when Z state is having one spin multiplicity, then we can have a total 9, because as all of you know, the G state can be 9, so 9 into 1 is 9. F state can be 7, so 7 into 3 is 21. D state can be 5, so 5 into 1 is 5. P state can be 3, so 3 into 3 is 9. And the S is non-degenerate, and therefore 1, and therefore 1 into 1 is 1. So if you make a sum total, it is nothing, comes out to be 45. So we can say that the 2d electron in the 5d orbital can be written in 45 different ways, which gives this type of an electronic states or microstates. Again, one can apply the Hund's rule and can get the ground term. Of course, in this case, there are two states having 3 spin multiplicity. So either of these two states will be ground state, but since the L value of F state is more, therefore triplet F will be the ground term, and therefore for D2 electronic configuration, triplet F will be the ground term. So therefore, when any electronic transitions are occurring in the metal complexes having D2 electronic configurations, then they will arises from the triplet F, because triplet F can split into triplet A1, triplet A2, triplet F can split into triplet T1, triplet T2 and triplet A2. Therefore, there will be various transitions will be possible. 3 electronic transition will be possible in such case. All of you have aware about the Orgel diagram. When we draw the Orgel diagram, it is possible to know how many electronic transition will take place in this particular metal ion having different electronic configurations. So in this case, as I told you, for D2 electronic configurations, we have a triplet F will be the ground state. Then the next first excited state will be triplet P, and then in increasing order we have a singlet G, singlet D, and singlet S. Singlet S will be the highest energy states in the electronic in the uh, singlet S will be the highest electronic state. So when the electron will jump from these states, you will get a different particular electronic transition. So here I have concluded the different configurations starting from P1 to P2 to P3, all these configurations, and we can have a D1, D2, D3, D all for various configurations. What will be the possible microstate will be there, and therefore what are the terms are possible for this have been tabulated well before. Out of this, one can always find out which one will be the ground term, how it will split into different ligand filled environment, and therefore depending upon that the different electronic transitions will be taking place. Of course, while the electron is jumping, one has to consider about the selection rules and also the ligand filled environment, which is changing the energy of these transitions. So this is all what we have to discuss in this lecture. So in summary, we have discussed there are three types of bands are observed in the transition metal complexes, namely spin allowed and spin and Laporte forbidden, while spin and Laporte allowed, as well as charge transfer transition. We have also seen about the MLMS and how it describes the individual microstate themselves, whereas the total angular momentum quantum number L and total spin angular momentum quantum number S describes the collection of microstates called atomic energy states. We have also seen about the orbital and spin angular momentum coupled to give resultant angular momentum J. I have also described the syntax for the term symbol, which are used to represent the electronic configuration and resultant angular momentum of an atom, that is 2s plus 1 Lj. And we have also seen that how can this be used to find out the relative energies of these states. For taking the particular example of the P2, that is to say we have a 3 microstates for P2 electronic configurations, and that can be extended further to any such electronic configurations, and one can always construct the states of different energy in particular environment, as we have done it in the case of D2. We have 5 different microstates. And finally, this is the institution of higher learning in the state of Gujarat, from where I belongs to, the Maharaja Sayajirao University of Baroda, which is in the state of Gujarat in the city Vadodara. A beautiful building of the arts faculty, and followed by the first line of our university anthem, namely Ame Vadodarana Vidyapithna Sapna Saravana. With this, I thank you for your patience hearing. This is my contact detail, my email address, as well as my cell number. If you have any queries or questions, you can always reach to me through this my contact detail. Thank you.